Okay, let's talk about pH. We've all seen it, right? It's on shampoo bottles, it's a distant memory from science class, maybe you hear about it when you're gardening. But what if I told you that this super simple number scale, from 0 to 14, is hiding a pretty powerful secret? A secret that kind of changes how we should think about everything, from the food we eat to the health of our entire planet. So let me start with a little puzzle for you. We all know a lemon is more acidic than a tomato. That's obvious. But by how much? You'd probably guess, a little bit more. But the reality is pretty staggering. A lemon with a pH of around 2 isn't just a tad more acidic than a tomato at a pH of 4. It's actually 100 times more acidic. How is that even possible? Well, the answer is tucked away inside the true meaning of pH. So the term pH itself, it comes from the Latin phrase potentia hydrogenii, which literally means the power of hydrogen. And that's exactly what it's measuring. The concentration, or you could say the power, of hydrogen ions floating around in a solution. The more of those hydrogen ions you've got, the more acidic something is. Simple as that. Most of us definitely remember this basic layout from school. Anything with a pH below 7 is acidic. 7 is perfectly neutral, think pure water, and anything above 7 is considered basic or alkaline. Seems pretty straightforward, right? But the real magic, and where a lot of the misunderstanding comes from, happens in the gaps between these numbers. So let's think about the difference between a pH of 4 and a pH of 5. I mean, on the surface, it's just one number. A small, what seems like an insignificant little step. But is it really just a small step? Or is it a giant leap in what's actually happening chemically? And here it is. This is the big secret. Every single whole number step you take on that pH scale represents a massive tenfold change in acidity. That means a solution with a pH of 4 is 10 times more acidic than one with a pH of 5. We're not talking about addition here, it's multiplication. And this difference just keeps compounding like crazy. Going from a pH of 6 down to 5, that's 10 times more acidic. But dropping from a 6 all the way down to a 4, that's 10 times 10, making it 100 times more acidic. And a jump from 6 to 3, that's a jaw-dropping 1,000 times more acidic. So, this is what scientists call a logarithmic scale. Now, that might sound super technical and complicated, but you're actually already familiar with this idea. It works on the exact same principle as the Richter scale for earthquakes, where a magnitude 6 quake is 10 times more powerful than a 5, or the decibel scale for sound. The pH scale just uses that same powerful logic for acidity. So the big takeaway so far is that a tiny change in a pH number is a huge deal in reality. But so what? Why does this really matter outside of a chemistry lab? Why should we care about this hidden power in our day-to-day lives? Well, it turns out it matters a lot. pH is an absolutely critical indicator in at least 3 huge areas: the taste and safety of the food we eat, monitoring the health of our environment, and making sure that industrial processes aren't poisoning our ecosystems. Let's start with food, because who doesn't love food? You know that sharp, zesty, fresh taste you get from citrus or a good yogurt? That's acidity. The pH level is what gives it that flavor, but it also acts as a natural preservative. It creates an environment where nasty bacteria just can't survive. That tenfold difference is the key to both how good it tastes and how safe it is to eat. Now, in the environment, pH acts like a vital sign for the health of our water. A seemingly small drop in a lake's pH, say from 6 down to 5, can be totally catastrophic for fish and all the other wildlife that live there. It's not just a warning sign, it's a critical alarm bell for ecological stress, often triggered by things like acid rain, pollution. And that, of course, leads us to industry. Any water that gets used in industrial manufacturing has to be treated before it can be released back into the environment. Its pH has to be carefully, precisely controlled to meet these really strict regulations, all to make sure we don't cause one of those devastating environmental shifts. So just think about some common stuff you probably have in your house right now. Lemon juice is sitting there at a pH of about 2, vinegar is around 3, pure water, that's our neutral middle ground at 7, and then you have something like baking soda, on the basic side, at about a 9. Now let's apply what we just learned about that tenfold difference to these items. Let's go back to the lemon juice and vinegar. That difference between a pH of 2 and a pH of 3 isn't just one little unit of acidness. Nope, that lemon juice is literally 10 times more acidic than the vinegar sitting in your pantry. That right there is the logarithmic scale in action. This crazy logarithmic power also changes how we have to measure things. You can't just take 2 different pH readings, say a 4 and an 8, and average them out to get 6. It just doesn't work that way. Because of those massive tenfold jumps between numbers, scientists have to report a median value or a range of values to give you a truly accurate picture. So ultimately, it really comes down to this. Having a deeper understanding of this simple little scale is essential. It enhances everything from our food safety to how we take care of our planet. Recognizing those giant leaps hidden inside these tiny steps is absolutely critical. So the next time you see a pH value on a label or in an article, you won't just see a number. You'll see the exponential power that's hidden inside it. And that kind of leaves us with a final thought. Now that you see the hidden power packed into this one simple number, what else are we measuring out there in our world that's way more powerful than it seems?